Good day, everyone. This is Dinesh here to present a seminar titled Connection Between Automata Theory and Number Theory. This essentially explains how automata theory and number theory work together. I will introduce you to two fields, number theory and automata theory. By connecting these two fields, we can gain insights into real-world problems, especially in technology and cryptography, and how automatas can help in solving mathematical equations and problems. This might sound a little complex, but at the end, you will see how these ideas fit together in a practical and more understandable way. Yeah. So, moving on, what is automata theory? Let's begin with automata theory. Imagine a set of machines or models that react to inputs with a series of rules. The simplest is a finite automata, which allows a fixed set of instructions, such as if this, then do that. This model is widely used in text searching, data validation, and basic control systems. As automata grow more complex, like the push-down automata and the turning machines, like turning machines are more complex than the both push-down automatas and finite automatas. By analyzing these, they helps us to solve more sophisticated problems. By analyzing these automatas, we gain insights into building efficient algorithms and managing complex tasks in computer science. This is like the foundation of computer science. Next, moving on to the number theory. Number theory, in contrast with automation theory, focuses on the problem properties of numbers themselves. It studies integers, prime numbers, and sequences and patterns to find out how numbers behave when patterns emerge and what makes certain numbers or unique, like numbers or sequences unique. For instance, prime numbers are building blocks of cryptography because of their rarity and unpredictability. Um, Number theory also explores modular arithmetic, often described as clock math, where only reminders matter. Understanding number theory is essential for fields like cryptography. And we will talk about more about cryptography in the upcoming slides. Why the intersection? Why combine automata theory and number theory? Combining these two fields seems strange at first because this is computer science based and this is mathematical based theories, but it's incredibly powerful. Automata as rule based machines helps us to find and analyze predictable patterns, helps us find and analyze predictable patterns, and the number theory has many problems that depend on recognizing patterns, thus make them a perfect partner. So, by you applying automatas and certain number sequences, we can detect patterns faster and even solve complex problems more efficiently than on paper. This collaboration especially useful in data security and understanding the structure of various number sets. Finite automata and arithmetic sequences. So, arithmetic sequences are to understand this concept, we should know what is arithmetic sequence. Arithmetic sequence are sequences that are created by repeating a specific rule. For example, it's a common example, Puma sequence. Each step involves flipping zeros and ones, creating a pattern that never repeats exactly the same. So, automata can easily generate and recognize such patterns, which is useful for coding and error detection because automatic sequence can ensure like reliable non-repeating patterns. Yeah. Then turning machines. As I talked earlier, turning machines are a more complex class of automatas which are doing in computing number theorem functions. They're also useful in determining the complexity of primary testing and factoring problems. This computational approach aids in understanding the inherent difficulty of various number theoretical tasks as mentioned in the slide, contributing to more to complexity theory, sorry. Then regular languages or and modular arithmetic. Regular sequences are patterns that incredibly repeat in a predictable manner, like a wallpaper with typical colors or colors or shapes like that. Automata are perfect for recognizing these types of sequences since they follow a set of rules. Automata can easily detect these things. Like they can compare other sequences. They can recognize repeated patterns easily and save space and time. So these actually makes them in aids in creating error checking systems. And also we are going to talk about model arithmetic. So this model arithmetic is also known as clock math, as we discussed earlier. This focus on reminders after division. Yeah, this only focus on the remainder after you divide a number with another number. For example, on a clock after 12, we start back at 1. So automata can detect these patterns within modular arithmetic. If you can say mod 8, after 8, it starts with the 9 goes, 9 changes as 1. So these automatas can detect patterns in cryptography since it helps in create secure data patterns. Model arithmetic is also used in computer graphics and error checking algorithms with specific patterns are required for uh, the more efficient use of these algorithms and for computer graphics as well. Okay, as we discussed earlier, the preliminary testing. This is actually used in cryptography, and this is used to increase efficiency. Automata-based models simplify prime checking algorithms by filtering out non-prime numbers in a computational effective manner, allowing secure protocols. Secure protocols. Yeah, preliminary testing is also used to increase efficiency and checking the efficiency to come up with more efficient data and such kind of things. Moving on, we are seeing about transcendence number theory, not a meta theory. These numbers, transcendent numbers, are pi that can't be numbers like pi that can't be expressed by simple equations like quadratic equations. Automata can't fully handle these patterns because they lack a clear repeatable pattern. However, they can help reveal some structures within these numbers. This is useful in applications like error detection and coding. This limited this limited ability to analyze transcendental numbers still provides insights about complex algorithms and encryption techniques. Yeah, the thing is, the transcendental numbers can't actually be completely analyzed or detected, but their ability to uh, analyze patterns is actually great. And moving on, we are talking about the famous pure fantasy equations, which require integer solution. These are like integral to the number theory. Automata models simplify approaches to solving these equations by breaking down complex relations between numbers, revealing patterns that can lead to systematic solution techniques that, that are not possible before these automata. Moving on, rational and irrational numbers in automata. Automata are excellent recognizing rational numbers which have like repeating or ending decimal. But the issue comes when we are dealing with irrational numbers like pi. Pi is an irrational number as we discussed, it's a transcendental number. These don't have repeating patterns. Automata can't fully process irrational numbers, but they're efficient with irrational numbers, which is useful in applications like periodic data analysis and error checking, where predictable repeating numbers are common. So, irrational numbers are like rational numbers. They're not so much, which automata can't be of so much use in those. But for rational numbers, it's very easy and more effective and more efficient in calculating those things. Moving on, the complexity of number theory and number theory problems. Some problems in number theory are beyond what automatas can solve. These are called undecidable problems and they don't follow predictable rules. For instance, figuring out unbreakable inscription relies on complex numbers theory problems that automata can't handle on their own. Recognizing these limits is important because it helps researchers focus on developing more sophisticated computational models and go beyond the capabilities of basic automata. So, like automatas, we know it faces a lot of limits, like in the Diophantine equations and transfer numbers, as we discussed earlier. Understanding these boundaries actually makes the scientists and the researchers develop to develop more efficient tools for tackling more intricate problems. Yeah. Now, applications in cryptography. Cryptography is a main part of the number theorem that uses automatas. These protects the information uses principles from both automata number theory. Prime numbers and model arithmetic creates keys that are hard to break. That's what makes the security factor of the cryptography. Automata helps check patterns and detect potential weaknesses. Automatas are used to detect whether these patterns or for instance, take passwords. Automata helps to see if it's easily breakable or not. Automata are used in such conditions to determine the weakness of a certain pattern and detect potential threats, and helps us to develop more encryption methods that are more secure. Yeah, we can build by using this, we can build a more secure encryption that keeps data safe from hackers and hackers. Yeah. Now, the current research, the open questions that we have about these theorems, these connections is uh, scientists and researchers are still exploring questions like whether automata can help us better understand transcendental numbers, like Diosynchronous equations, and improve algorithm for complex encryption. These areas are still being developed, and advancements could have revolutionized revolutionized on how we handle data and solve number theory problems. By deepening our understanding, we may unlock entirely new applications in data security and number theory problems. So, to conclude, the link between automata theory and number theory offers powerful tools for analyzing patterns and solving complex problems. Automata gives a structured way to examine sequences, properties in numbers, which have applications in data security, pattern recognition, and more. The collaboration of these fields shows us how different areas of math and computer science can come together to tackle big challenges. So that's it. Thank you for the attention. Uh, Moving on, these two papers helped me a lot in doing this slides. The first one especially, a great paper that explains the relation between automata number theory by Adam. So yeah, thank you.